Hello everybody, and welcome to the final video of the real analysis lectures, at least for now. I guess you could consider this sort of part of a first course, a first introduction course to real analysis. And today we will be covering the fundamental theorem of calculus. Although maybe fundamental theorems of calculus, there's like two versions. And I mean, if you've taken calculus, you might have seen this before. And of course, we're just going to be proving the theorems. And what this is going to do is relate the derivative and the integral, right? So the two analysis things that we've defined and worked with over the past couple of lectures, right? Because again, remember that we started using a lot of the topology stuff, right? We started with defining the real numbers and then looking at their topology, and then we define these two things, right? The integral and the derivative for real valued functions, and now we're going to be able to relate the two ideas. So without further ado, there's no definitions. We already have everything we need. We're just going to get right into the theorem, or theorems. So the first one, right, so I'm going to label this as FTC1. So this is the first version of the Fundamental Theorem of Calculus. It says, suppose f is a Riemann integrable function on the interval AB, and suppose there's a function f such that the derivative of f of x, or capital F of x, is equal to little f of x for all x in our interval AB. Okay? Then what does this tell us? This tells us that the integral from a to b of f of x dx, little f, is equal to capital F of b minus capital F of a. So just to sort of recap what this theorem is saying, it's saying that if we're integrating a function and we have some other function that its derivative is the function that we're integrating, then the integral is just the difference of two values for the bigger function, right? The function that the antiderivative, right? We would call capital F an antiderivative of little f of x. Okay? So the way we're going to prove this is by we're going to use the techniques from the Riemann integral videos, right? So we're going to start with a partition, and we have to show that as the partitions get smaller and smaller mesh, the value of the Riemann sums are approaching f of b minus f of a. Okay, so we're going to start with a partition P of our closed interval AB. What should I say here? The mean value theorem gives evaluation points, right? So points in the partition intervals from xi minus 1 to xi, such that f prime evaluated at the evaluation point is equal to the difference quotient over this interval of capital F I minus xi minus 1, and okay, so this is just straight from the mean value theorem on capital F of x, and this is equivalent to, right, so capital F prime is the same thing as little f of x, right, just by our hypothesis on the theorem. So we have f at the evaluation point, and then xi minus 1 is the same thing as delta xi. Okay? And so this is going to be equal to f of xi minus f of xi minus 1. So what this means is that our Riemann sum for the function little f and the evaluation points that we've chosen here from the mean value theorem is going to give us, right? So what is this? This Riemann sum is just by definition f at the evaluation points times the changes in x, right? The lengths of the partition intervals. And then using this equality that we have here, we get that this is f of xi minus f of xi minus 1. And this is a telescoping sum, right? This is going to be, right, if we plugged in I equals 1, we would get f of x1 minus f of x0. And then the next term would be f of x2 minus f of x1, right? And so on and so forth. And so this telescopes, right? So we have all these intermediate terms canceling out. So this was a minus. And so we get f of xn minus f of x0. But of course, these are f of b and f of a, right? Because the start and end values, x values of the partition, are the start and end values of the interval, namely a and b. And so any partition has evaluation points such that the Riemann sum over those evaluation points equals f of b minus f of a. Thus, as the mesh of P goes to 0, right, we must have that the Riemann sums are approaching f of b minus f of a, regardless of evaluation points. Right? Because as your partitions get finer and finer, right? The you can think of it as each subinterval is sort of approaching like 1 point, right? And by the mean value theorem, inside of those subintervals, you have to have some point where, you know, this equality is true. And since your intervals are shrinking and shrinking and shrinking, right, you always have to have one of those evaluation points. It follows that this equality is going to be, you know, it may not be true for every evaluation point, but it's going to become closer and closer for as your intervals are getting smaller and smaller. Okay. But the main idea, right, and this holds in a lot of contexts, is that if you can find, if you know that for any partition, right, any partition, you can choose evaluation points such that your Riemann sums are going to be some fixed value, that then you have to have that the integral of f over that interval is equal to that value. Okay. So a bit of a technical result there at the end, but hopefully you can understand why that's the case. Okay, so now we are just gonna get right into the second version, right? So FTC2. What the second version is going to say is that if we start out with f being a continuous function on the interval a to b, and we are going to define a function capital F of x to be the integral from a to x of f of t dt, right? So here we're using t for the integral because x, the variable of capital F, is in the integral, right? It's over a varying varying thing for, and so x here is going to be defined for a in a to b. And remember that continuous functions on a to b are Riemann integrable, right? We've proved this before. Okay. Okay, what now? Okay. So these are the hypotheses. And so this is going to say that the derivative of this function that we've just defined, capital F of x, is equal to little f of x, the continuous function, for all x in AB. Okay, so let's get into the proof. And the proof here is not going to use the sort of integral ideas, right, like the last proof did. This proof instead is going to use more limit and derivative rules. Okay, so we want to sort of just calculate the derivative of f of x, right? And the way we do that is by looking at, of course, the limit sh approaches 0 of f of x plus h minus f of x over h. Okay? And we're just going to plug in the definitions here, right? So f of x plus h is this integral here, and then f of x is this integral here. And we know from integral rules that this difference of integrals, since we're integrating the same function, so what this is going to do is actually subtract out the interval from a to x, and what we're going to be left with is the integral from x to x plus h of f of t dt. Okay? Now, call in video 13, we proved that if a function g of x is bounded on the interval c to d, then we know that the integral over c to d of g of x dx is bounded by two things, right? So the length of the interval, and then the actual function values that the function is bounded by. And so what this actually says is that in our case, right, is that thus, so suppose that f of x is bounded similarly, then we know that this integral here is going to be bounded by, well, the length of this interval from x to x plus h is just h. So this is going to be bounded by little m times h and capital M times h. Thus, little m is bounded by here this quotient, the integral of f over h, x to x plus h is less than or equal to m. So the value of this quantity, right, the integral of f over h, is bounded in the same region that the values of f of x are bounded, right? But these are the bounds of f on a very small interval, right? So as as h approaches 0, m and little m and capital M will approach f of x, right? Because then, right, the interval from x to x plus h is just going to approach the point x, and so f of x, right, its minimum and maximum values are just f of x, right? So, thus, as h approaches 0, right, we have f of x is less than or equal to this quantity So the limit as h approaches 0 of this integral over h is equal to f of x. And this quantity, right, as we showed, is equal to the derivative of capital F at x. And so therefore we have shown what we want to show, right, which is that the derivative of capital F of x is equal to lowercase of f at each value of x, right? So notice that here this x is fixed, right? H is actually what's changing here. We're actually using h to manipulate what's happening, right? Because, right, this interval from x to x plus h, what's changing is that h is approaching 0, and so this interval is just approaching the singleton set containing x. And therefore, the min and max values of f is just one value, which is f of x. Okay? So, you know, it's really cool that both these theorems, right, are connecting the derivative and the integral. And they're telling us two different things, right? They're telling us that if we know, basically to integrate the derivative of a function, we just subtract the values of that function. And to take the derivative of an integral, right, we just get the function that we're integrating. And the proofs of these two different theorems use the ideas, the different ideas that we've sort of dealt with, right? The first theorem used partitions and sums, Riemann sums, and then the second proof, the proof of the second theorem used difference quotients and limits and the actual limit definition of a derivative, which I think is pretty cool. So yeah, that's it. I hope y'all enjoyed this series. Like I said, I'm not very sure if I'll return to analysis at a later date, but next on the agenda is abstract algebra, starting with groups and then rings and then fields. So yeah, I'll see you then.